which is due to Gross-Again-Colli-Wagen, that if the order of vanishing of the L series of an elliptic curve over Q is less than 1, then the BSD conjecture is true. Yes?
Can you turn on the light?
Okay, I turn on this light. So that the order of vanishing of the L series is equal to the rank of the elliptic curve as is predicted by the BSD conjecture. Now, we saw that this proof used essentially the modularity of E, the fact that E appeared in the Jacobian of a modular curve. And there was one remark I forgot to make yesterday, so I want to start by making it now, that this proof works basically without change, works almost without change, or extends, for the case of an abelian variety quotient of the Jacobian of J naught of n. So without change for these abelian varieties A sub f, which we discussed last week in the context of Mazur's theorem and the proof of Merel's theorem. And that leads to, so all the ideas are the same, you just have to work with a larger endomorphism ring. And that leads to the fact that if the L function of A sub f at 1, which is equal to the Hecke L series attached to the modular form f, is non-zero, then AF of Q is finite. In particular, that's a special case of that result. And that was exactly what we needed, if you remember last week when we discussed Mazur's theorem. That's exactly what we needed to produce a good quotient of J naught of n with finite model V group. And that was used crucially, I mean, in the proof of Merel's theorem that was discussed by Marussia and Boledo. Okay. What is that? Oh, you're sorry, yes. I mean, right. So the product of overall the embeddings of KF into Q. Yeah. You're right. So it's related. I mean, these two things are if one is non-vanishing, and so is the other. Yeah, that's the correct. Okay. Okay, so then, okay, after having discussed this... yes, because you see this Colli-Wagen construction, it works with Heegner points on the modular curve, and it maps them down to the elliptic curve by the modular parametrization. But the degree zero divisors supported on Heegner points give rise to elements in J naught of n, right? And so you can also project them to these quotients A sub f.
Yeah, sure, but these formulas for the norm will not be valid,
no?
Now the Heegner operator is not just multiplication by A or
Oh yes, but I mean that's why I say you have to work with the endomorphism ring. So what's going to come up is an AL, right? A coefficient AL, which is the Fourier coefficient of the modular form. Now that belongs to some finite extension of the rationals, the field generated by the Fourier coefficients. But this finite extension of the rationals can be viewed as the or is certainly contained in the endomorphism algebra of this A sub f. And so you can make sense of the norm relations. Everything goes through with a bit of extra technical complication arising from the fact that your endomorphism ring is a bit bigger. But it's sort of really the same ideas. In fact, this was done by Colli-Wagen Logachev in a paper. I mean. So I wanted to mention that because that sort of ties up a loose end from last week when we sort of proved this theorem of Mazur and then Merel modulo the existence of this quotient for which you could prove the finite sigma of A group. What is? Oh yeah, I mean, this is the product. Okay. Product of the complex embeddings. Okay, so now what I want to do. Okay, so then I mentioned that at the end of my last lecture, sort of the motivation for what came yesterday and what's going to come today was to understand whether if E is an elliptic curve defined over a more general number of fields. So you see that there are many, of course, many nice Diophantine applications of knowing something about the Bertrand and Dyer conjecture for elliptic curves or abelian varieties, obviously. So you would like to have this kind of results also over number fields. So if E over F is defined over, so is an elliptic curve defined over a number field F, what can we say? Can we prove a similar result? So can we prove a similar result? And we saw that the answer, or at least we developed enough of the kind of machinery yesterday to get a hint that probably the answer will be yes for many elliptic curves defined over totally real fields. So if F is a totally real field, then I'm going to say that E is said to be arithmetically uniformizable. Okay, and I'll just denote that by AU from now on. AU if there is a Shimura curve, if there exists a Shimura curve X over F, such that E appears in the quotient as a quotient of the Jacobian of this Shimura curve over F. Okay, so such that, of course, there's a non-constant morphism from the Jacobian. So that you can find your elliptic curve in the Jacobian of some Shimura curve. Now, if an elliptic curve is arithmetically uniformizable, that implies that it's modular, and it corresponds to a modular form. I didn't actually define precisely what it means for an elliptic curve to be modular. It means that the L series of the elliptic curve is equal to the L series attached to some other object, namely a modular form over this totally real field. But what I want to sort of remark on is that unlike the case of the rationals, where these two notions are equivalent, you do not have the reverse implication. Okay? So there are, I mean, we expect that all elliptic curves are modular, but there are certain elliptic curves which are not arithmetically uniformizable that do not appear in the quotient of any Shimura curve. So that's a problem because
If something is modulo over C, is modulo over F.
yeah,
That's what we do for the ordinary.
yes, that's true. I'm not completely sure. I would have to think about that. I think that there might be some subtle points about, yeah. 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 So now, I mean, basically, the theorem, which one could prove by sort of using the CM points on Shimura curves and so on, and analogs of, so this is a theorem that's due to a number of people. Certainly, it relies on the extension by Zhang of the Gros-Zagier formula and work of Kolivag and Logachev on the sort of descent side of this strategy, so to speak. The theorem is that if E is arithmetically uniformizable, then we have the same statements, right, for the elliptic curve, that the order of vanishing of the L function is less than 1. That implies that the rank is equal to the order of vanishing. Okay? But, okay, so now I just want to mention that, of course, there are still a lot of mysteries in spite of this. This is a very nice result. It applies to a much larger class of curves than we had before. So I want to kind of mention two questions, which are going to be more the motivation, actually, for this afternoon's lecture by Matt Greenberg. So suppose that, so the first mystery is the case where F is a real quadratic field. This is sort of the simplest example of an elliptic curve which is not arithmetically uniformizable. So if F is real quadratic and E has everywhere good reduction, and let's see, and or is a twist, has everywhere good reduction, or is a twist, a quadratic twist of such a curve. Then, in that case, one can show that E is not arithmetically uniformizable, so this theorem doesn't apply. In that context, we do have some partial results. So we know that if the order of vanishing at s equals 1 of the L function of E over F is 0, in other words, the L function doesn't vanish, then E of F is finite. And this is a result that was proved independently by Tian and Zhang, and also independently by Longo. So we have this implication for analytic rank 0. And the idea here is that even though the elliptic curve E is not present in the Jacobian of any Shimura curve, we can use the theory of congressively modular forms to show that the mod P to the n representation can be found in the mod P to the n representation associated to some Shimura curve, and then carry through Coley-Wagens's descent for this abelian variety, which is related to E via the fact that it has the same mod p to the n torsion. So that's sort of the idea. Yes. Right. So it's a kind of argument based on congruences because of the fact that we don't have this elliptic curve is not sort of geometrically present in any Shimura curve. But the mystery is, what about the case of order vanishing 1? Then, of course, yes, 1. If the order vanishing is 1, then we expect there to be a point. But then congruences are not enough somehow. We would really need this elliptic curve to appear on a Shimura curve in order to produce a point of infinite order. The other mystery, which is completely wide open, is the case where F is an imaginary quadratic field. And that's going to be really the subject of Matt Greenberg's lecture this afternoon. Okay. But, okay, so the point I want to make, so you would like to be able to say that there are structures analogous to Heegner points in more general settings than just elliptic curves over totally real fields. And so I want to kind of first motivate that kind of expectation by revisiting Heegner points from the point of view of the Birchett and Dyer conjecture. So let me just say a few things about kind of Heegner points revisited. So if I have so I have my elliptic curve, and I'm going to place myself in the most traditional classical setting, which we discussed at length, the case where E is an elliptic curve over Q and appearing as the quotient of the modular curve x naught of n. Now, in that case, we saw that there was this Heegner hypothesis that implied that we had this kind of construction of points over various abelian extensions of K. So if L is split in K for all L dividing n, then we have Heegner points. Okay? Now, you can try to understand that. I mean, the fact that there's this large supply of points over abelian extensions of this quadratic imaginary field, K, can be understood from the point of view of the BSD conjecture because, well, so if H is any ring class field of K with discriminant prime to n, so I take any ring class field of K with this property, then I can consider the L function of E over H. And the Birchett and Dyer conjecture tells me that the order of vanishing of this L function should be the rank of E of H, right? Well, this L function, because E is defined over Q, therefore certainly over K, this L function factors as a product over characters of the Galois group of H over K of the twisted L series L of E over K chi S. So you have this factorization over the H complex characters of the Galois group of H over K. Now we can study the functional equation of this L function. The general yoga of functional equations also works for twisted L series, and it tells us in this context that the L series of E over K chi S is related to the L series of E over K twisted by chi bar at S, at 2 minus S. The central point of a functional equation is S equals 1, but you have this chi bar coming up. But because H is a ring class extension, and because E is defined over Q, if you just stare at the Euler factors defining this L series, you'll see that it's actually equal to the L series of E over K twisted by chi at 2 minus S. These two L series are the same. It's because the two-dimensional representation of the Galois group of H over Q, which is induced from chi, is the same as the induced representation of chi bar. I mean, that's a two-dimensional representation with real values. So we have that. And so therefore, this L series is related to its value at 2 minus S. And under the Heegner hypothesis, one can show that the sign is always minus 1. So each of these factors vanishes to odd order. And that means, so parity, in this case, tells us something very precise about the order of vanishing. It tells us that the order of vanishing of the L series at S equals 1 is greater than the degree of H over K. And that leads to the expectation by the BSD conjecture that the rank of E of H should be conjecturally greater than this degree. And that's something that, of course, we cannot show that, but the Heegner construction gives us good candidates for points which in some suitable kind of asymptotic sense fill up a large part of these Mordell-Weil groups. So we kind of have a good way of attacking the problem of constructing this systematic supply of points, constructing them.
If you split up the Mordell-Weil group over each character component,
Yes.
is it conjecture that the rank of each character component is equal to the order of vanishing of the corresponding twist?
Yes. Yes. There's a kind of, sort of combination of the BSD conjecture, the kind of Artin, with the Artin formalism that predicts that, yes, that exactly what you expect would happen, right?
Has that
Yeah.
been proved in any instance?
Oh, yeah. It has been proved. So there's a similar statement to the one I wrote up here, right? For the order vanishing at most 1.
Yeah. But in the higher order of vanishing.
No, okay, so I'll tell you what we can prove. I mean, we can prove that if the order of vanishing of the L function of E over H S is equal to H over K, is equal, not just greater or equal, as I have here always, then the rank of E of H is what you would expect, namely the degree. That you can prove. And it's a kind of extension of Colli-Wagen's theorem to characters. And, so, I mean, yeah. So that much we know. But that's not really a higher rank case of BSD, right? It's really a rank 1 case in disguise. One should not view it as a higher rank because we have this Galois action floating around. Yeah, I guess. I mean, well, it's nice to know, but yes, right. No, so yeah, absolutely. This kind of a phenomenon is very useful. For example, also in the context of function fields, it allows you to show that the rank of elliptic curves over function fields, and not necessarily isotrivial, can be arbitrarily large. So that's something. So there are kind of nice applications in some cases of this kind of large growth of Mordell-Weil. Okay. So but what I want to talk about now, the mystery that I want to talk about in today's lecture, is that this analysis of signs goes through basically unchanged if K is real quadratic. So if K is real quadratic, the analysis of signs goes through without any extra complication. And the simplest case of this kind of phenomenon is the case where we take a real quadratic field, real quadratic K, in which, and we assume that the conductor of the elliptic curve is of the form P times M, where P is a prime that doesn't divide M, and we have the kind of the following modified Heegner hypothesis. The modified Heegner hypothesis is that for all the primes L dividing M, L is split in K, so that's the same as the usual Heegner hypothesis. But the prime P is required to behave differently, namely P is inert in K. So this is actually very similar to the original Heegner hypothesis, if you think about it, because in this original Heegner hypothesis, the field is quadratic imaginary. So all the primes dividing the conductor split, but the prime at infinity is sort of inert, so to speak, right? Here, all the primes, including the infinite prime, are split, but this prime P, which we've singled out, is inert. If you make the analysis of local signs, you find that exactly this kind of phenomenon occurs. So that we expect the rank of E over any ring class field of the real quadratic field to be at least the degree. And of course, we would like to understand that, that phenomenon. Okay, so what I'm going to outline, so what I want to outline now is a conjectural formula for these points, so they should behave in all respects like Heegner points, but they have this kind of ghostly existence. I mean, we can't show that they exist. So in that way, they're a bit like Stark units. I mean, as Christian would agree. And so I call these Stark Heegner points in this case. And the main interest, maybe, of this Stark Heegner point construction in the context of this lecture series is that it suggests very strongly, it gives strong experimental evidence, not much theoretical evidence, but at least good experimental evidence that the kind of structures that are present to prove these theorems towards BSD for special classes of number fields should probably exist for other number fields. And that'll be developed more. I mean, here I'm staying with an elliptic curve over Q. I should insist that my elliptic curve of conductor N is defined over Q, but this afternoon we'll see cases where this construction can be adapted to other number fields, most notably imaginary quadratic fields. So the construction is going to proceed in several steps. I mean, the first thing I should mention about the construction is that it's a p-adic construction. And naively, you might expect that from the fact that in this modified Heegner hypothesis, the roles of p and infinity have been interchanged. And also, if you wonder for the first time why there aren't Heegner points attached to real quadratic fields, well, you learn that Heegner points are images of points in the upper half plane, which are quadratic irrationalities. But there are no real quadratic irrationalities in the upper half plane because they all go to the boundary. Okay, but once you see that, given that you learned yesterday that there are also p-adic uniformizations of Shimura curves, it's very tempting to replace the complex upper half plane by a p-adic upper half plane, because now that since p is inert, there are plenty real quadratic irrationalities living on the p-adic upper half plane. So we would like to kind of squeeze out an invariant from these real quadratic irrationalities that we could say is sort of plays the role of the Heegner points. Now, it doesn't work to consider Shimura curves. So Shimura curves don't give you this, and there are many reasons for that. Shimura curves will not contain these Stark Heegner points. And I want to give you a kind of, there are many reasons why the naive idea of just taking real quadratic points on HP, then mapping them to a Shimura curve by the p-adic uniformization is really wouldn't work. Yeah?
I'm just bewildered. Is there any meaning we should carry in our mind with this word Stark?
It's by analogy with Stark's conjectures. So Stark sort of constructs these units in certain abelian extensions of number fields from leading terms of Artinel functions. And the feature that this construction shares with Stark is that the conjecture is very concrete. You can compute these leading terms, exponentiate, and then get units. This is something that you can talk to Christian about that. It's a sort of a big, fascinating set of conjectures, but we have no tools to actually construct these units. And this is going to be exactly the same thing with these Stark Heegner points. We're going to write formulas for them. We have computer programs that will calculate them, but we can't actually show that they exist. Yes, and right. So that's true also that you can sort of view this. I mean, certainly I've been motivating it in the sort of the framework of Euler systems, or this kind of structure that's used in Colli-Wagner's argument is what's known as an Euler system. And there are Euler systems of units as well, and conjectural Euler systems of Stark units. And this is a kind of another one of these conjectural things. Okay, so let me just justify why you could not hope to find these things in Shimura curves. Well, the reason is that we expect that there are infinitely many real quadratic fields of class number 1. Okay? We can't prove that, unfortunately, but we certainly expect that it's true. We expect that at least 2/3 of the real quadratic fields are class number 1. So if there was a Shimura curve X, which contained this nice system of Heegner points satisfying the same sort of phenomenology as classical Heegner points, we would get a Shimura curve X endowed with an infinite number of real quadratic points corresponding to real quadratic fields of class number 1. But the kind of sort of natural extension of Merel's theorem for Shimura curves, which is actually much simpler in that case, would lead you to expect that these curves in general have only finitely many quadratic points or degree d points for any fixed d once the curve gets complicated enough. And so you really wouldn't expect to find these points on a curve. You have to go a little bit beyond curves. I mean, that's the idea. Okay, so that's just a kind of remark. Now, let me just describe the construction. So the goal now is I'm going to give you a map. Okay, so let me set up some notations, actually. So I'm going to define a subgroup by analogy with the p-adic uniformization of Shimura curves. In this context, I'm going to let gamma be the subgroup of 2 by 2 matrices, but with coefficients in SL2Z of 1 over p. So I invert the prime p. This is by analogy with the construction of the kind of groups that uniformize Shimura curves, where you have to take a quaternion algebra, take an order, and then invert the prime p, as we saw in Matt's lecture yesterday, for example. So we take these things, but then we kind of impose a sort of gamma. We want to make an analog of gamma naught of m. So m is the prime to p part of the conductor of the curve. So we suppose that m divides c. Okay, so this is a group which acts by Mobius transformations, both on the classical upper half plane and on its p-adic avatar, its p-adic analog. Okay? Yeah.
If C is like m over p, do we consider that as m dividing C?
Yes, I mean that, so the C is a p unit, but it makes perfect sense that m divides C. I mean m divides the numerator, right? So, yeah. Yeah, because m is prime to p. I mean, there's no p in m. So this group acts both on H and HP by Mobius transformations, but it's a kind of bigger group than the ones we had before in the context of p-adic uniformization, and it doesn't act discretely on either of these upper half planes. It acts actually has dense orbits, but it acts discretely on the product. So the action of gamma on HP cross H is discrete if you endow these with the natural topologies. So the idea is so what we're going to do, so the goal is to define a map, which I'll sort of call phi, for lack of a better name. And it's going to be defined on the set of points on the p-adic upper half plane with real quadratic coordinates, and it's going to be really defined on the gamma equivalence classes of points with real quadratic coordinates on HP. And it's going to take values, conjecturally, I should say. Well, it's going to take values in E of CP. But it's going to kind of conjecturally take values in E of K-ab. And we're going to conjecture that this collection of points we get here behaves in all significant respects like classical Heegner points. So that's sort of the goal. I want to show you how you define this map. I should say first that the definition will be analytic. So the definition of this map phi is going to be a purely analytic definition. That's not to say that the map phi is analytic on HP in any sense. There's going to be a kind of, you can already see that from the fact that gamma has dense orbits. This map does not extend to a rigid analytic function on HP, but we'll see that it is defined via computing integrals of certain rigid analytic functions that I'm going to construct for you, which are associated to the modular form.
So what is E? E is an elliptic curve or a cube?
Exactly. E is an elliptic curve. This is this context that I put myself here. I'm in the simplest case. So I have a real quadratic field. I have an elliptic curve over Q of conductor P times M. And P is a prime. Yeah, so I have these kind of conditions. And in that case, I want to kind of give you a recipe for constructing certain local points, which conjecturally will be Heegner points attached to the real quadratic field. So the construction goes in several steps. The first step is to exploit the modular symbols, which were already introduced in previous lectures, and we heard about them in the context of the proof of Merel's theorem, for example. So modular symbols, I remind you simply that so F now is going to be the classical modular form. Okay, so This is the classical modular form on H mod gamma naught of n, which is associated to E. And if we take 2 points in P1 of Q, which we think of as cusps on the modular curve, or as points on the completed upper half plane, then I can define a function, depending on these 2 things, by essentially taking the integral from R to S of the differential form f of z dz. Okay? Now, that's a complex number, but if I take its real part and I divide by a suitable period, which is essentially the Néron period up to some power of pi or something, but there's some fixed transcendental period which I can choose in such a way that this quantity belongs to C. And I can normalize it in such a way that the modulo values, if you want, has no common divisor, which sort of pins it down essentially uniquely. So I have this modular symbol. This is the one that played an important role in the calculations of Maroussier-Reboledo when she explained Merel's theorem. I should mention here that the fact that these values are actually in Z follows from the fact that the modular form f has integral Fourier coefficients. And this is really just, this period is essentially the Néron. So this is essentially, you can think of it geometrically or topologically as the image of the geodesic joining R to S on the completed upper half plane in the homology of the modular curve, and then you take of the elliptic curve. So you have the modular parametrization, which maps this upper half plane to E. You look at the image of this path in the homology of the elliptic curve, and maybe kind of multiplied by some small integer to close the path. Okay, so this is an integral invariant. And really, this is the main object that we're going to need. And now I have a theorem, which is essentially elementary, but allows me to transform this modular symbol into a collection of measures on P1QP. And it's sort of the main, although it's completely elementary, it's kind of the main passage in a way in this construction. It's the main, so this is a proposition. So the proposition is that, well, this is sort of step 2, I guess. Step 2, I'm going to construct a collection of p-adic measures using this modular symbol. So there is a unique system of measures on P1 of QP indexed by the pairs of cusps, by pairs RS in P1 of Q, okay, and denoted denoted mu RS. So I have a collection of measures depending on 2 parameters, R and S. And these measures are characterized uniquely by the following 3 properties. The first property is that I want to tell you what mu RS does. What's the value of this measure on 2 basic compact open subsets. The first one is the total space. And the total measure is required to be 0. This is what we also heard in Matt Greenberg's talk. It's a bit surprising when you're used to classical measure theory, but we have to remember that these measures are assumed to be p-adically bounded, but there's no positivity condition coming along with this. And so this doesn't imply that this set is negligible anyway. Okay, so the total space has measure 0. But then the relation with the modular symbol is that the value of this measure on the basic compact open subset ZP, so I identify P1QP with QP union infinity by taking the standard coordinate. And then this is a standard compact open in P1QP, and I require that this measure be given by my modular symbol IF RS. So this completely determines the value of these measures on these 2 sets. Then I impose a gamma invariance condition on these measures. So now I'm going to use this group to kind of pin down the measure further. And so I require that mu, the measure associated to gamma r, gamma s of this compact open gamma u is equal to mu rs of u for all gamma in gamma, rs in P1 of Q, and U compact open in P1 QP. Okay? And then the third condition I want to require is that this measure behaves like a modular symbol. So if I take mu rs and I add mu st, I should get the measure associated to the pair mu rt. And that's the main reason why I'm denoting this function of two variables with an arrow between the r and the s, is to give the idea that there's a kind of integration from r to s going on, and that this natural additivity condition is satisfied. Okay, so that's the proposition. And the proof, this is one of these propositions where the statement is much longer than the proof. And the proof is actually very simple. You just use the fact that gamma acts transitively, or essentially transitively, on the open balls in P1QP. It's not quite transitive. The action is, there are two orbits. But then I've pinned down the value of the measure on two of these compact opens, and that determines the value of gamma everywhere, I mean the value of mu st everywhere from this gamma invariance property. That's all there is to it. So if you know the modular symbol, you know all these measures. So the third step in the construction is one that you were certainly expecting if you think about what I described yesterday about this sort of essential bijection between gamma invariant measures on P1QP and rigid analytic functions on the p-adic upper half plane, which are sort of weight 2 for the action of gamma. And that's, of course, we're just going to take the same p-adic transform, sort of this kind of what Teitelbaum calls a p-adic Poisson transform, to turn these measures into a collection of rigid analytic functions. So I define some function which I'll call FRS of Z by taking the integral over the boundary of the function 1 over Z minus t against the measure d mu rs of t. So what I get now from this is a collection of rigid analytic functions indexed by these pairs of cusps, but these things but the same calculation, which if you did the exercise of yesterday where I asked you to show the invariance properties under gamma, you'll see that FRS transforms like a modular form of weight 2, but not quite. So if I write gamma as so I have this kind of transformation behavior. F gamma r gamma s of az plus b over cz plus d is equal to cz plus d squared times f rs of z for all gamma equals a, b, c, d in the group gamma. So this kind of looks, it's not a single, I mean, if you had a single rigid analytic function which was invariant under gamma, that would be the constant function, because gamma is too large a group. It acts with dense orbits on the p-adic upper half plane. But by introducing these extra pair of variables, you sort of salvage that, and this collection is sort of what plays the role in the p-adic world of the modular form associated to the elliptic curve. Okay, so now we can, of course, write down integrals, as we did yesterday. We can write down Coleman-style line integrals for these functions. So I'm going to define, well, I'm going to consider the integral from tau 1 to tau 2 of f rs of z dz, which I remind you from yesterday. So in order to integrate a rigid analytic form, which is given in terms of a measure by this kind of formula, you just have to consider the integral over the boundary of the function log of z minus tau 2, or maybe t minus tau 2 over t minus tau 1, d mu rs of t. So t now is the integration variable. This is the formula. So you can take this as a definition of the Coleman line integral. Again, note that this depends. I've made a choice here in defining this integral. I've chosen a p-adic logarithm. And shortly we'll be making a precise choice of the p-adic logarithm. For now, this log is any p-adic logarithm. Now, because these measures, mu, rs, are all z-valued, this integral admits a multiplicative refinement, as we saw yesterday, by formally exponentiating everything. That's sort of the definition in terms of Riemann sums of this integral. And so I have also a multiplicative integral from tau 1 to tau 2 frs of z dz, which is defined in the obvious way. Okay. Now, if you look at this line integral, this p-adic line integral, you kind of, the feeling of it is that it's sort of defined by a series of two integrations. Because in defining frs, I've already sort of taken the modular symbol associated with the classical modular form integrated from R to S. So there's sort of a complex line integration going on, and then we kind of transfer to. So one can introduce a notation which turns out to be very suggestive, and it's sort of the right notation for thinking about these p-adic line integrals. Which is that we'll sort of denote this, so notation. I'll write the integral from tau 1 to tau 2 frs of z dz. I'll write it instead as the integral from tau 1 to tau 2, integral from R to S, omega f. That's my notation. So this is what when I write this, I mean this. So what is this f? What is this omega f? So omega f is nothing really. It doesn't mean anything by itself. It just kind of appears as a placeholder in the notation. But you should think of this as, for those of you who know about Hilbert modular forms, you can think of this as being kind of a mock Hilbert modular form on the quotient HP cross H mod gamma of weight 2, 2. Okay, so if you don't know what these things mean, don't worry about it. I'm not going to use that. It's a kind of maybe sort of philosophical motivation for some of the formulas that are going to come later. So these period integrals, the point is that they behave formally like those of a Hilbert modular form of weight 2, 2. And we can't make sense formally of what we mean by such a mock Hilbert modular form. And this terminology is due to Maser, actually. So mock. It is a philosophical statement.
You can't make sense. Is that a theorem, or is there a...
Oh, yeah, maybe. Maybe someone with a better analytic skills than me could kind of make, yeah. I'm not saying that we will never make sense. I'm saying that I, right now, cannot make sense of it. Okay. But you see, it's a bit like when you talk about distributions, right? When you go pass from functions to distributions, you don't really care about the object as a function. You just care about being able to integrate it. And in this case, this is exactly this. Certainly this makes complete sense mathematically. It's a very precise definition. Okay, so that's all I wanted to say about step 3. Only to mention that, okay, what are the formal properties of this integral, of this double integral? The integral from tau 1 to tau 2 rs omega f plus the integral from tau 2 to tau 3 integral rs omega f is equal to the integral from tau 1 to tau 3 rs omega f. So it's sort of additive in both. In the first set of variables and the second is fixed. Likewise for the second set of variables. Okay, so it sort of behaves like a double integral, right? Rs integral from tau 1 to tau 2 st omega f is equal to the integral from tau 1 to tau 2 st rs st rt. Yes, rt omega f. So you have this kind of additivity in both sets of integration variables. And the third property, which is the most important, is that this is globally gamma invariant. So if you take the integral from gamma tau 1 to gamma tau 2, integral from gamma r to gamma s omega f, that's the same thing as shifting all the 4 variables of integration simultaneously. Okay? And that's exactly, for those of you who know about it. What is that?
Where
the values of the measure, yeah, well, they're z-valued, these measures. They take values in z because of the modular symbol takes z values. So in particular, you can think of them as p-adic measures. I mean, you can certainly. Oh, the functions are CP valued. They're CP valued. I mean, of course, they're rigid analytic functions on HP. Yes, have an integrality property. Yeah, that's used. Yes, definitely. I mean, yeah. Yeah, I mean, well, there's an answer to that question, but it's a bit long, so we can talk about it after or something. I mean, there are variants and so on where you can push the analogy in different directions. And, well, yeah. Okay. So now I want to kind of write down, so now I go to step 4, I guess. So step 4 is a stage of the construction which is not purely formal, unlike the previous stages. So now I'm going to choose the branch of the logarithm in a special way. So I'm going to choose my logarithm in such a way that it's 0. So remember that to choose a branch of the logarithm essentially amounts to choosing a uniformizer of CP. I mean, an element of the ring of integers of CP with strictly positive p-adic ordinal. And then decreeing that element is 0, that log is 0 on that element. So I'm going to take the element which is 0, I'm going to take it to be q. So log q equals 0, where q is the Tate period of E. So the q is the Tate period of this elliptic curve. And that turns out to be a crucial choice for the following theorem, which would not be true otherwise. So the theorem now. Oh, I forgot to mention, I mean, so as a last piece of notation, I mean, of course, I have also something which I'll call the multiplicative integral, Rs omega f, which I just define by replacing the additive integrals by their multiplicative analogs. And the relation between the two is that the multiplicative integral, the logarithm of the multiplicative integral, is just the usual additive integral. Okay? And this one does not depend on any choices. But now I choose my log so that it has this property. And then we have a theorem, which is actually due to Ralph Greenberg, I should say, because there's another Greenberg in the audience. So Ralph Greenberg and Glenn Stevens. And the theorem says that there is a unique function from HP cross P1 of Q cross P1 of Q, which I'm going to denote by the following symbol. Tau Rs goes to and this function satisfies, so this is a unique, CP value again. It takes values in CP. Satisfying the following conditions. The first condition, so they're going to be kind of analogous conditions to that one. It's going to be a condition that relates this sort of integral where I've omitted one variable of integration here. So the relation is that the integral tau 2 Rs omega f minus the integral tau 1 Rs omega f should be the integral from tau 1 to tau 2 integral Rs omega f. Okay, so there's this relation between this kind of indefinite or semi-indefinite integral, sometimes it's called the semi-indefinite integral, and the definite integral via this formula. Okay, so that's one property. The second property is a gamma invariance, as we had before. So we want this sort of function where we split off, in some sense we've split off the integral into two pieces. Well, we want this piece to be invariant under gamma. Okay, so we want that the integral gamma tau, gamma r, gamma s omega f is equal to the integral tau rs omega f for all gamma in gamma, and all endpoints, of course, that you could choose. And then finally, the third condition is that you want this to still behave like an integral in the second set of variables of integration. So you want that this plus integral from, so r to s, s to t, should be the integral from r to t. Okay? And, I mean, okay, those of you who are a bit experienced will recognize that somehow lurking in the background of this statement is kind of the fact that one could associate a certain cocycle, and the proper way of saying that would be to associate a certain 2 cocycle to this function, and then we're saying that, and it would be a CP star valued cocycle, and we said that when you apply the log, this particular branch of the p-adic logarithm, a certain cocycle splits, becomes trivial. And that's sort of the contents. But we have this function, which is completely well defined. And I won't say anything about the proof, if only to say that really the beef in this proof is really an earlier result of Greenberg-Stevens, which relates the p-adic period of the elliptic curve, the Tate period, to certain derivatives of p-adic L series. And if you kind of take their statement and rewrite it in some way, then you find this result, this theorem. So now, the final step, step 4 in the construction, step 5, I guess, is to actually, now I can define the Stark-Heegner point. So now I give myself a point tau in the p-adic upper half plane intersected with k. And I observe that because this tau is real quadratic, the simple calculation shows that if I look at the stabilizer of this point tau in the group gamma under Mobius transformations, this is a group of rank 1. And it's generated, so by a single element, which I'll call gamma sub tau. So it's a cyclic group generated by one element. Of course, there's an ambiguity in the choice of this gamma tau, and there are ways of kind of making certain normalizations so that that you have a kind of unique choice of generator. So you choose some generator of this stabilizer subgroup, and then you define a p-adic period, j tau, to be simply the integral for this tau, and then r to gamma tau r. So you choose some r in P1 of Q, some base point, and then you define j tau to be this in CP. In fact, you can even do a bit better. You can define sort of a multiplicative integral. So there's a refinement of this theorem, which is actually a bit conjectural, which says that the corresponding multiplicative integral would split modulo Q to the z. So you can also define a kind of semi-indefinite multiplicative integral, which would take values this time in CP star modulo Q to the z. And you pass from one to the other by taking the logarithm. But this one carries a little bit more information. Okay, and now I define my point, P sub tau, to be the image under the Tate uniformization. I think what Matt Greenberg, for example, called phi Tate yesterday in his lecture. So I take this phi Tate of j tau star. And, okay, that's it. So the conjecture is that the collection, so this is what I'll call phi of tau, I guess. Is this phi Tate of j tau star? It belongs to E of CP. But in fact, if you really look carefully at the definition, because my points tau live in K, they belong to the quadratic unramified extension of QP. So the integrals are all between points which live in the quadratic unramified extension of QP. So in fact, or the completion of K at P. So this really belongs, in fact, to E of KP. It's not quite so, in such a huge field. It belongs to E of KP. And so the conjecture is that the collection of these points of phi of tau, as tau ranges over the collection, over HP intersect K, behave in all respects, and I don't really have time to make this very precise, but all the properties that you saw for classical Heegner points, like a Gros-Zagier formula, Colli-Vagas theorem and so on, should hold for these norm compatibilities and so on, would hold for these points. So in all respects, like Heegner points, except that now they're defined over abelian extensions of the real quadratic field. Okay. Okay. Yes, so good point. So this is an exercise. It's actually a fun exercise. I was planning to give it, is to show that J tau does not depend on the choice of R. This period, J tau, and J tau star also, of course. I mean, so this you make a choice of base point, but then in the end your invariant does not depend on that choice. And it's a consequence of these formal properties of the indefinite integral that I wrote down here. That's actually a fun exercise. It's not hard.
The definition of J tau star across the second integral is the integral from R to gamma tau R?
Yes, I'm sorry. Yes, sorry, it's the same thing. Gamma tau R. I just kind of take the multiplicative version of this one. So I kind of, all I want to say here is that there's a kind of natural lift of this invariant CP under the logarithm. The logarithm is not injective, so you lose a bit of information when you apply the logarithm. Namely, there's an ambiguity, which is essentially the torsion in the CP star. And you don't want that ambiguity, so there's a way of making a more careful definition where you really get a kind of God-given point in KP star, and that's very useful in computations. Theoretically, you could say, well, it's not very different. I mean, a p-adic point or define modulo torsion, but really it's very important when you want to do numerical verifications that you have this finer invariant. And it's important to be able to do numerical verification because you have so little theoretical evidence for this conjecture. So now I just want to kind of conclude this discussion by mentioning evidence. So there's a lot of numerical evidence. In fact, if you look on my webpage, you'll find a package of computer programs that will allow you to compute these Stark-Heegner points for quite large class fields. I mean, the largest class field I've done is of degree 23 over the real quadratic field. And in a few seconds, it will produce coordinates of points. And sort of it's available. You can do it very quickly for any elliptic curve of conductor less than 100. And you could add elliptic curves too. So there's a lot. I mean, we've done calculations of literally hundreds or maybe thousands even of these Stark-Heegner points by now.
This conjecture in particular means that your point on the elliptic curve belongs to Hilbert class?
Yes. Yeah, the Hilbert class field or the ring class fields. You have to associate to every tau a certain order. We look at the stabilizer of tau in the matrix ring M2 of Z or M2 of Z of 1 over P or something. You get a certain order in a real quadratic field. And the field of definition should be precisely the ring class field associated to that order. So by varying the tau, you're going to get really collections that land in all kinds of abelian extensions of the real quadratic field. In fact, they should generate essentially the full kind of, or a half of the maximal abelian extension of the real quadratic field. The whole. What is that?
It's not proven.
Absolutely not. Absolutely. This is really a conjecture. I mean, you mean this kind of construction? Of course, sort of the analog of the construction with K is imaginary quadratic is this sort of a classical Heegner construction where you use complex integration. Yeah, the p-adic thing will certainly fail. I mean, there are the number of points. For example, in the stabilizer, I've used the fact that the stabilizer is cyclic of rank 1, and that, of course. So the format doesn't quite, yeah. There's a strong analogy between the two things, but somehow complex analysis here is being replaced by p-adic analysis. It's reflected by the fact that now the inert prime in the situation is p and not infinity. Okay, so we have a lot of numerical evidence, and there's a small piece of theoretical evidence, which is a theorem that I proved with Bertolini some time ago. And that says that if the class number of K is equal to 1, or in fact not even, if tau 1 up to tau h are a complete set of points on HP intersect K of conductor 1, so that the conjecture predicts, so up to the action of gamma, so H here is the class number of the real quadratic field K. So you have this collection of H points. The conjecture predicts that each of these guys, their image under phi is defined over the Hilbert class field, and the trace should be defined over K. Should be a point in E of K. And that much we can prove. Then phi of tau 1 plus phi of tau h is equal to a global point, p sub k, in E of k, modulo perhaps a small ambiguity, which is the torsion in E of kp. So up to some torsion point in E of kp, you can show that this analytic invariant is indeed a global point. But only when you trace down. The fact that the individual points are algebraic seems to lie much deeper.
In this case, it's not true that phi of each tau is
Yeah, you can't show, I mean, these are, for all we know, transcendental things, although the computer always tells us they're algebraic. But we can show that the sum at least is algebraic and defined over the field that you would expect by the Shimura reciprocity law, so to speak.
Can you show formally that these points are satisfying
No, I mean, I can write down a Shimura reciprocity law, but showing that would be just as, I mean, of course, it would be it's the same depth. I mean, in fact, it's equivalent to showing that, Oh, yeah, and I should say also that not only that, but then this point pk is a non-torsion if and only if the derivative of the L function of E over k at 1 is non-zero. So that's part of the theorem. Okay? So we can also show that this point satisfies the same phenomenology as Heegner points in this respect, which is in a sense the bad news because it means that you only are getting at elliptic curves in rank 1 situations. Okay? Yeah, you're right. You're right. You're right. Yes. Right. I mean, if you want, yeah. Okay. Okay. So that completes what I wanted to say in today's lecture. I just want to finish with the remark that really, as well, are kind of parallel to the classical Heegner point construction, but sort of maybe, at least for now, seem to lie beyond geometry. We don't have the kind of geometric structures that allowed us to consider CM points. And once you have this construction, you can kind of go by analogy and extend these things to number fields. So in the two things I mentioned at the beginning of my talk, the case where E over F is defined over F, and F is a real quadratic field, or in fact a totally real field of a real quadratic field. You can actually get conjectural points in this case as well, and the idea here is simply to replace the mock Hilbert modular form, okay, by a genuine Hilbert modular form, by a genuine Hilbert modular form. So the idea is that once you see these notations and so on, it suggests that you should also do the same thing with periods of classical Hilbert modular forms. And in that way, you can construct points, I mean conjecturally, by purely complex analytic means, which you cannot do by any geometric method because there are no Shimura curves. And that was work, the sort of experimental work that I published a few years ago with Logan in this context. And there's some also interesting ongoing work of Charolois in the context of Eisenstein's theories, which relates this construction to Stark units, to more classical objects like Stark units, and makes maybe more precise the analogy that I suggest with the terminology between these Stark-Heegner points and Stark units. And in the second case, where F is an imaginary quadratic field, is going to be discussed in the lecture by Matt Greenberg this afternoon. And we'll see that somehow this formalism also suggests a way of constructing points. This is actually following ideas of Matt Greenberg himself and Mac Trifkovich. So he'll present some work which gives a nice concrete method for conjecturally constructing points on elliptic curves over imaginary quadratic fields, which should behave like classical Heegner points. So this concludes my lecture series, and I just want to kind of wrap up the whole thing by making a comment about the entire lecture series. So what I did was to present a very quick overview of some of what I view are the highlights of the theory of curves in the earlier lectures, at least in the first 8 of my 10 lectures. So we saw Falting's theorem last week. Then after discussing Falting's, I discussed the proof of Mazur's theorem on modular curves and the theorem of Merel. on degree D points on modular curves. And then at the end of last week, we discussed Weil's theorem on Fermat's on the Fermat equation, on Fermat's last theorem. And this sort of corresponded to the half of my lecture series devoted to curves of genus strictly bigger than 1. And then in the second week, I focused on curves of genus 1, and then the main topics discussed were the BSD conjecture and the sort of approach of Gross, Zagier, and Kolyvagin to understand the BSD conjecture via Heegner points. Okay, so these are kind of, but then we saw also that these topics are very much related, and that many of the ideas which we saw in the first week, abelian varieties, Galois representations, modular forms, and so on, sort of pervade all of these major results. Okay, so I just want to end by sort of making a critique of my lecture series, which is that certainly the pace was a bit frantic, and it was sort of analogous to these package tours of Europe that you sometimes see where you visit 5 capitals in 10 days. And I just want to finish by saying that I hope that this has given you the desire to revisit some of these landmarks and at a more leisurely pace and with more details. So thank you for your attention.